Can a star be proven single? Observational limits and theoretical implications. Boris, Kriger. Institute of Integrative and Interdisciplinary Research, Department of Astrophysics. Abstract. The classification of stars as single or binary is a cornerstone of stellar astrophysics, yet it rests on an asymmetry that is rarely stated explicitly. While binarity can be positively established through observation, the absence of detected companions cannot constitute proof of true singleness. This article argues that, for any individual star, it is in principle impossible to assert with certainty that it is not part of a binary or higher-order system. This impossibility is not merely technical or instrumental, but epistemic in nature. By examining the limits of observational methods, the structure of parameter space for stellar companions, and the physics of star formation, we show that single star is not a physical category, but a provisional observational status. Keywords: binaries, general stars, statistics, stars, formation methods, observational catalogs. 1. Introduction. Modern astronomy routinely distinguishes between single and multiple stars. Catalogs list vast numbers of objects classified as isolated, and theoretical models often treat singleness as a default or simplifying assumption. Yet this practice conceals a fundamental epistemological problem. To observe a star and declare it binary is to make a positive claim supported by detected signatures. To observe a star and declare it single is to make a negative claim based on the absence of such signatures. These two statements are not epistemically symmetric. The central claim of this article is deliberately modest but strict. No observation of any individual star can justify the conclusion that it is not binary. This is not the claim that all stars are in fact binary, nor that singleness does not exist in nature. It is the weaker, but more defensible claim that singleness is not observationally decidable in the same way binarity is. What follows is an analysis of why this asymmetry is unavoidable and why it should be taken seriously. B. The desert. Observational criteria and their limits. All methods used to detect stellar companions operate within constrained observational windows. Direct imaging depends on angular resolution, contrast limits, wavelength, and distance. Spectroscopic detection relies on radial velocity variations that vanish for unfavorable orbital inclinations, long periods, or near equal mass ratios with circular orbits. Astrometric methods lose sensitivity for very long period companions, or for systems with small reflex motion. Transit and eclipse detections require specific geometric alignments that occur only for a small fraction of systems. Even the most stringent observational constraints leave parameter space unexplored. This Carmini study of GJ486, Caballero et al. Represents perhaps the tightest limits on stellar singlicity achieved to date, combining high-precision radial velocities, adaptive optics imaging, and astrometric data to exclude companions across a wide range of masses and periods. Yet even this exceptional case cannot claim completeness. Very low-mass companions at certain orbital configurations, or massive companions at extreme separations, remain consistent with the data. As Caballero, 2026, Private Communication notes, there can still be low-mass companions that we have not found yet. Crucially, the failure of a method to detect a companion does not imply that no companion exists. It implies only that no companion exists within the method's sensitivity domain. Even the simultaneous absence of signals across multiple techniques merely narrows the allowed region of parameter space. It never eliminates it entirely. For every excluded configuration, infinitely many remain compatible with the data. Thus, observational astronomy does not deliver the proposition this star has no companion, but only the weaker statement. No companion has been detected within the explored observational regime. Conflating these statements is an interpretive leap, not an empirical conclusion. The conventional assumption that a star is single until demonstrated the opposite, Ribas et al. 2023, inverts the proper epistemic ordering. It treats non-detection as evidence for a strong negative claim that the data cannot support. Dwightham. The structure of binary parameter space. The space of possible binary configurations is effectively continuous and unbounded. Companions may be arbitrarily low in mass, from stellar remnants to brown dwarfs or planetary mass objects. Orbital separations may range from contact systems to distances so large that orbital periods exceed the duration of modern astronomy. Orbits may be nearly face-on, suppressing radial velocity signals, or nearly circular, minimizing time-variable effects. Luminosity contrast may be extreme, rendering companions observationally invisible against a bright primary. Importantly, there is no natural lower or upper cutoff in this space, imposed by fundamental physics that coincides with observational thresholds. The absence of detection, therefore, never corresponds to an empty parameter space, but only to a partially excluded one. Singleness is not a point in parameter space. It is a boundary claim that cannot be reached by finite observational exclusion. Window. Play start. Star formation and prior expectations. Independent of observational limitations, star formation theory further undermines singleness as a default assumption. The collapse of molecular clouds is generically unstable to fragmentation. Angular momentum conservation, turbulence, and gravitational instabilities naturally produce multiple bound condensations. Observational surveys of young stellar objects confirm that multiplicity is common, particularly at early stages, Duchesne-Krauss 2013. While dynamical evolution can disrupt some multiple systems, leaving apparently isolated stars, this does not convert observational non-detection into proof of intrinsic singleness. At best, it shifts prior expectations, making undetected companions more or less likely. The epistemic structure remains unchanged. Likelihood can increase or decrease, but certainty remains unattainable. 5. Angus. Epistemic asymmetry between detection and non-detection. The core philosophical point can now be stated clearly. Detection is a positive existential claim. At least one companion exists with properties within a detectable domain. Non-detection is a failure to establish such a claim. It is not evidence of non-existence unless the space of possibilities has been exhaustively ruled out. In the case of stellar companions, this exhaustion is impossible in principle, not merely in practice. This introduces an epistemic asymmetry that is often obscured by linguistic convention. Binary star names a discovered structure. Single star names the absence of a discovery. Treating these as parallel physical categories is therefore misleading. One is an object-level classification, the other is a statement about observational limits. Beer. W. Document. Implications for stellar modeling. Recognizing the non-decidability of singleness has practical consequences. Models of stellar evolution, disk dynamics, and planet formation that assume isolation may inadvertently ignore perturbative effects from undetected companions. Increasingly, astrophysical anomalies attributed to internal stellar processes are reinterpreted as signatures of past or present binarity. Sana et al. 2012. This perspective does not demand that every model explicitly include a companion. It demands epistemic honesty about what single means. Not a physical certainty, but a working hypothesis adopted for calculational convenience. 7. Extended implications. The recognition that stellar singleness is not observationally decidable has several concrete and conceptual consequences that extend beyond a terminological correction. First, it alters how stellar catalogs should be interpreted. Entries labeled as single do not describe a physical state of isolation, but a current absence of detected companions within known sensitivity limits. Treating these labels as definitive properties risks reifying an observational gap into a physical attribute. Catalog statistics, therefore, should be read as lower bounds on multiplicity rather than as balance counts between single and multiple stars. Second, it affects stellar and planetary modeling. Many theoretical frameworks assume isolation by default, particularly in stellar evolution, rotation, magnetic activity, and disk dynamics. If undetected companions are epistemically admissible in all cases, then deviations from idealized single-star behavior should not automatically be attributed to internal physics. Hidden binarity becomes a legitimate alternative explanation, not an ad hoc complication. Third, it has implications for exoplanet studies. Planetary system architectures, orbital misalignments, eccentricities, and long-term stability are often modeled under the assumption of a single central star. Acknowledging that singleness cannot be established forces greater caution in interpreting planetary dynamics and formation histories, particularly for systems that appear dynamically perturbed without an obvious cause. Fourth, the result reshapes probabilistic reasoning in astronomy. Claims such as most stars are single cannot be strictly observational conclusions, but only statistical inferences under explicit priors and detection models. The impossibility of confirming singleness at the individual level introduces a structural uncertainty that cannot be averaged away. 8. The role of the sun. The sun occupies a peculiar and influential position in discussions of stellar singleness. It is often treated, implicitly or explicitly, as the paradigmatic single star. This status, however, is not the result of a fundamentally different epistemic situation, but of historical familiarity and observational convenience. From an observational standpoint, the sun is among the most intensely studied stars. Its proximity allows for levels of scrutiny that are impossible for distant objects. Yet even in this exceptional case, absolute singleness cannot be established. Companions with sufficiently low mass, extreme orbital separations, long periods, or unfavorable dynamical configurations remain observationally admissible. Deep infrared surveys have excluded Jupiter mass companions beyond 10,000 Rolet AU, but brown dwarfs at wider separations or in specific orbital phases remain consistent with current data. Historically, the assumption of solar singleness has shaped stellar theory. Because the sun was taken as a standard, models of stellar structure and evolution were built around isolated stars, with binarity treated as a perturbation or special case. This historical inversion is epistemically revealing. The most familiar star became the conceptual baseline, not because its singleness was demonstrated, but because it was convenient to assume. Recent reinterpretations of solar system anomalies have revived interest in the possibility of a past or present solar companion. The clustering of orbital elements among extreme trans-Neptunian objects at NOES, first noted by Trujillo-Shepard, 2014, and extensively debated since, has prompted hypotheses ranging from an unseen Planet 9 to more radical proposals involving a distant stellar or substellar companion, Beitigen et al. 2024. While the Planet 9 hypothesis posits a 510 Earth mass object at 400,800 Australian dollars, alternative models have explored whether a low-mass brown dwarf or even a primordial black hole at greater distances could explain the observed clustering and other dynamical peculiarities. The Oort cloud structure provides additional, if indirect, constraints on past companions. N-body simulations suggest that a stellar mass companion in the Sun's birth cluster, subsequently lost through dynamical ejection, could have shaped the outer solar system's architecture, including the Oort cloud's extent and the scattered disk population. Pordagiswart 2024. The hypothesis of a solar sibling that shared the Sun's natal environment, and later dispersed, is consistent with the observed chemical homogeneity of solar-type stars in the solar neighborhood, and with dynamical models of cluster dissolution. The Sedna problem exemplifies how apparently single-star dynamics may require revision. Sedna's extreme orbit perihelion at 76 Australian dollars, aphelion beyond 900 AU is difficult to explain through known planetary perturbations alone. Proposed explanations include a past close stellar encounter, a still-present distant perturber, or capture from another star's planetary system. Each hypothesis invokes companionship, whether transient or persistent, as a necessary explanatory element. The assumption of perpetual solar isolation struggles to account for such features. The Sun also plays a subtle psychological role in discussions of stellar singleness. Because no companion has been detected despite extensive searches, there is a strong temptation to regard this absence as conclusive. Yet this is precisely the epistemic error highlighted throughout this article. The Sun does not escape the general rule. Exhaustive non-detection is not possible when the relevant parameter space is open-ended. Its case strengthens the argument rather than weakens it, by showing that even maximal observational attention cannot close the question definitively. In this sense, the Sun is not an exception to the argument of this paper, but its most instructive example. If even the nearest and best observed star cannot be certified as single, and if its planetary system's architecture may itself encode the signatures of past companionship, then the claim of singleness for any other star is necessarily provisional. Dakakuri. Anthropic bias and the appearance of singleness. The apparent prevalence of single, life-hosting stars introduces an additional layer of selection that must be addressed: anthropic bias. Even if binary and multiple systems are intrinsically common, observers capable of reflecting on stellar architecture necessarily arise only in environments that permit long-term stability and biological evolution. Binary systems, particularly close or dynamically active ones, can be less hospitable to life. Gravitational perturbations may destabilize planetary orbits, induce extreme climate variability, or inhibit the long-term stability required for complex biology. As a result, life-bearing planets may be statistically rarer in strongly interacting binaries than around effectively isolated stars. This introduces a powerful selection effect. Observers are more likely to find themselves orbiting stars that appear single or weakly perturbed, regardless of the true underlying distribution of stellar multiplicity. The observational fact we are around a star that seems single, therefore carries little evidential weight about how common genuinely single stars are in the universe. Ward Brownlee 2000. Crucially, this anthropic filtering does not require that the host star be truly single. It requires only that any companions, if present, be dynamically distant, low mass, or otherwise non-disruptive on biological timescales. Such companions would be precisely the hardest to detect observationally. Tendo. Multiplicity and evolutionary disruption. The impact of binarity on the emergence and persistence of life is not merely additive, but multiplicative. A system containing two stars does not simply introduce one additional source of disturbance. It doubles the number of massive gravitational actors whose evolution, variability, and interactions can influence any surrounding planetary system. Each star in a binary system undergoes its own evolutionary trajectory. Stellar winds, magnetic activity cycles, luminosity evolution, flaring behavior, and eventual post-main sequence expansion occur independently. The presence of two evolving stars therefore increases the probability that at least one will pass through a phase hostile to biological stability. From an anthropic standpoint, this asymmetry matters. Observers are far more likely to arise in systems where the number of independent disruptive agents is minimized. Apparent singleness thus becomes a selection filter. Not because single stars are intrinsically common, but because systems that behave like single stars over long timescales are statistically favored for life. 11. Inclusiveness without exclusiveness in binary statistics. Statistical statements about stellar multiplicity are meaningful only in one direction. The inclusiveness of binary statistics, claims about how many stars are found to have companions within specified observational limits, is empirically well-defined and scientifically robust. The exclusiveness of such statistics, claims that a certain fraction of stars are truly single, is not. Multiplicity surveys legitimately establish lower bounds. When a study reports that a given percentage of stars are binaries, it states that at least this fraction exhibits detectable companions within the sensitivity domain of the survey. Such results are cumulative and convergent. Improved instruments and longer baselines systematically increase the measured multiplicity fraction. Raghavan et al. 2010. The Carmini Survey of M dwarfs, Cifuentes et al. Dalton 25 exemplifies this pattern. Combining high-precision radial velocities with adaptive optics imaging, it reveals companions in parameter space inaccessible to either technique alone, pushing multiplicity fractions upward from earlier estimates. Similarly, interferometric surveys of massive O and B type stars using VLTI gravity continue to discover previously undetected companions at separations of 1100 mass, corresponding to orbital periods from months to decades. Reggiani et al. 2025. Sana et al. 2014. These discoveries occur among stars extensively studied by spectroscopy for decades, demonstrating that well-characterized systems routinely harbor hidden companions. Each such discovery converts a putatively single star into a confirmed binary. No discovery ever converts a confirmed binary into a proven single. Exclusiveness, by contrast, is structurally unstable. To assert that a star is single requires the exclusion of all possible companions across all masses, separations, orbital configurations, and evolutionary states. No finite survey can accomplish this. As observational reach expands, stars previously classified as single are routinely reclassified as multiple. The category of single stars, therefore, has no comparable permanence. It is continually eroded by improved detection, but never definitively secured. 12. Uneven epistemic claims. The preceding analysis leads to a decisive conclusion. Claims about binarity and singleness are epistemically uneven. They do not stand on equal logical footing, even when presented in symmetrical statistical form. A claim that a star is binary is a positive existential statement supported by concrete observational signatures. It asserts the presence of a companion within a defined domain and can be independently confirmed, refined, and retained as knowledge. Once established, such a claim is stable against further observation. In this sense, binarity is an affirmable property. A claim that a star is single, by contrast, is a negative universal statement. It asserts the absence of all possible companions across an open-ended parameter space. Such a claim cannot be established by finite observation. It remains perpetually vulnerable to revision, not because of technological immaturity, but because of the structure of the inference itself. D. Deloniel. One-directional revision. The epistemic asymmetry discussed above has a concrete and observable consequence. Revision proceeds in only one direction. Stars can move from the category apparently single to the category binary, but not in the opposite direction. There is no corresponding mechanism by which a star, once identified as binary, can be revised into proven singleness. Well-known cases illustrate this asymmetry. Bright, nearby, and extensively studied stars, Betelgeuse being a canonical example, have long been treated as single based on the absence of detected companions. Yet even in such cases, the literature repeatedly revisits the possibility of binarity as new data, methods, or interpretations emerge. This one-directional structure explains a familiar historical pattern in astronomy. Objects once thought to be solitary are progressively reclassified as binaries or higher-order systems as observational power increases. The reverse process, reclassifying a confirmed binary as truly single, does not occur. 14. Binarity as the rational default. Taken together, the preceding arguments justify a shift in perspective. Binarity may be rationally suspected as the rule rather than the exception. This does not assert that all stars are binary, in fact, but that binarity is the epistemically safer default assumption when reasoning about individual stars. Because singleness cannot be established, and binarity can, the burden of justification is asymmetrically distributed. To assume binarity requires only the admission of an undetected companion within an open parameter space. To assume singleness requires the implicit exclusion of all such possibilities. From a methodological standpoint, the former is always the weaker and more defensible commitment. Importantly, this does not collapse into an unfalsifiable claim that every star has a companion. The claim is conditional and epistemic. Given what can and cannot be known observationally, treating stars as potentially binary is more consistent with both data and inference than treating them as definitively single. Misdav. The vast blind spots of binarity detection. The rational suspicion of binarity is reinforced by the sheer scale of the observational blind spots involved. The regions of parameter space in which companions are detectable form narrow, discontinuous windows embedded within a vastly larger domain in which binarity is effectively invisible. Blind spots arise along multiple independent axes. In mass, companions can fall below detection thresholds while still exerting long-term dynamical influence. In separation, both very tight systems and extremely wide systems evade detection for different reasons. In inclination, entire classes of binaries produce minimal radial velocity, or astrometric signatures. In luminosity contrast, a faint companion can be completely submerged in the glare of a bright primary. Crucially, these blind spots are not expected to vanish with technological progress. While instruments improve, they do so within finite observational frameworks, limited mission durations, finite baselines, bounded resolution, and practical constraints on wavelength coverage. There is no trajectory toward exhaustive coverage of an unbounded parameter space. The zero parents. Black holes as binary partners. Among the most profound contributors to the blind spots of binarity are black holes. As companions, they represent an extreme case in which mass can be substantial, while observational visibility is minimal or entirely absent. Their existence sharply illustrates why binarity cannot be excluded even for the best-studied stars. A black hole companion may contribute no detectable light across most wavelengths. Unless it actively accretes matter, its presence must be inferred indirectly through gravitational effects alone. If the orbit is wide, nearly circular, or weakly coupled, even these effects can fall below detection thresholds. The parameter space for star-black hole binaries is far larger than the narrow subset represented by X-ray binaries or gravitational wave detections. Those systems are detectable precisely because they occupy rare extreme regimes. The overwhelming majority of possible configurations, wide or quiescent systems with long orbital periods, produce no dramatic signatures. 17. Double black holes and epistemic opacity. Double black hole systems represent the most extreme form of epistemic opacity in stellar multiplicity. Unlike star-black hole binaries, these systems can be entirely detached from electromagnetic observability for essentially their entire lifetimes. The LIGO-Virgo-Kriger collaboration has now detected over 200 compact binary coalescences through gravitational waves, with the O4 observing run 20232825 revealing an increasingly diverse population of black hole binaries with masses ranging from 5 to over 100 solar masses, Abbott et al. 2024. These detections confirm that double black hole systems are not rare curiosities, but a substantial component of the stellar remnant population. Crucially, gravitational wave detections sample only the final moments of binary evolution, the in-spiral and merger phase. The detected systems represent a tiny fraction of the total population, those whose orbits have decayed sufficiently to merge within the age of the universe. Wide double black hole binaries with orbital periods of centuries to millennia remain completely invisible to both electromagnetic and gravitational wave astronomy. Their separation is too large for significant gravitational wave emission, and they produce no light. These quiescent systems may vastly outnumber the merging population. Recent population synthesis models calibrated against LIGO-Virgo detections suggest that the Milky Way alone may harbor tens of millions of stellar mass black hole binaries, the overwhelming majority of which will never merge within a Hubble time. Garden et al. 2024. If even a fraction of these systems are bound to luminous stellar companions in hierarchical configurations, the implications for stellar multiplicity statistics are profound. The absence of detected companions around field stars cannot exclude membership in such higher-order systems. This has decisive implications for claims about stellar singleness. If double black hole binaries can exist undetectably in such numbers, then the absence of any observed companion around a luminous star does not even exhaust the possibility that the star is part of a higher-order system involving compact objects. Multiplicity does not require visibility. The gravitational wave window has confirmed the existence of a dark stellar population. It has not and cannot reveal its full extent. 18. Concealment of the true stellar population. The existence of vast, observationally inaccessible classes of binaries has a deeper implication. It may conceal a substantial fraction of the true stellar population. What is commonly referred to as the stellar census is, in reality, a census of luminous survivors, not of all stars that have formed or still gravitationally participate in stellar systems. Massive stars evolve rapidly and often end their lives as black holes or neutron stars. If such remnants remain bound in binaries or higher-order systems, they effectively disappear from electromagnetic observation. Entire evolutionary branches of the stellar population thus become invisible, not because they no longer exist gravitationally, but because they no longer emit light. The consequence is that stellar population statistics derived from luminosity functions systematically underrepresent the true number of stellar endpoints. Massive stars that once dominated star formation regions may leave behind remnants that persist for billions of years as gravitational actors without radiative signatures. King et al. 2012. 19. Contribution to the missing mass paradox. The concealment of large populations of compact binaries and dark stellar remnants naturally raises a further implication. Such systems may contribute non-negligibly to the missing mass problem at galactic scales. While they do not resolve the dark matter problem in its entirety, they complicate the clean separation often assumed between luminous matter and genuinely non-baryonic dark matter. Black holes, neutron stars, and other compact remnants are baryonic, but effectively dark. If a significant fraction of massive stars end their evolution in long-lived, electromagnetically silent binaries, their mass remains gravitationally active while being absent from stellar luminosity counts. Gravitational wave observations now provide direct constraints on this population. The LIGO-Virgo merger rate estimates, combined with population synthesis models, suggest that the total mass in stellar mass black holes within the Milky Way may exceed 10 Alonge solar masses, comparable to the mass in giant molecular clouds. Cecilia et al. 2024. Recent Gaia astrometric discoveries of dark companions to luminous stars have begun to reveal this hidden population directly. Gaia BH1, BH2, and BH3 black holes of 10, 9, and 33 solar masses respectively, detected through the wobble of their stellar companions, represent the tip of an iceberg. Gaia Collaboration 2024. These systems have orbital periods of months to years, placing them in parameter space inaccessible to gravitational wave detection and only marginally accessible to radial velocity surveys. The discovery rate suggests that quiescent black hole binaries are far more numerous than previously assumed. From this perspective, part of the missing mass may be not exotic, but unseen rather than non-existent. The paradox then becomes layered. There is missing mass relative to luminous matter, and within that, there may be missing stars objects that were once luminous, are still massive, but are now observationally silent. This does not negate the need for non-baryonic dark matter, but it weakens overly sharp dichotomies between visible stars and invisible mass, and it underscores how profoundly incomplete our census of stellar endpoints remains. 20. Population bias toward long-lived dwarfs. The cumulative effect of the arguments developed here is a systematic bias in our perception of stellar populations. Observational astronomy is structurally biased towards small, long-lived stars, particularly low-mass dwarfs, while the true number and historical influence of massive stellar objects are likely underestimated. Low-mass stars live for billions to trillions of years and remain steadily luminous over cosmic timescales. They dominate stellar catalogs not necessarily because they are overwhelmingly more numerous at formation, but because they persist. Massive stars, by contrast, burn brightly and briefly. Their lifetimes are short on cosmological scales, and their endpoints rapidly remove them from the observable stellar census. The consequence is a distorted statistical picture. Star population distributions inferred from current observations are weighted toward objects that are long-lived, faint, and stable, precisely those most likely to remain visible for billions of years. Massive stars appear rare not only because they are intrinsically fewer, but because they are transient and self-erasing from an observational standpoint. 21. The inaccessibility of true stellar statistics. The cumulative consequence of observational blind spots, evolutionary attrition, binarity, compact remnants, and anthropic filtering is stark. There is no principled way to reconstruct the true stellar population statistics of the universe. What astronomy can estimate is not the population of stars as such, but the population of stars that remain luminous, detectable, and dynamically expressive within narrow observational windows. Population synthesis models attempt to bridge this gap, but they do so by assumption rather than observation. They extrapolate backward from visible survivors, impose initial mass functions, multiplicity fractions, and evolutionary pathways, and infer what must have existed. Stanway Eldridge 2019. These reconstructions are coherent, but not verifiable. They are constrained narratives, not measurements. The implication is not merely practical, but epistemological. The true stellar population is not hidden in a way that awaits better instruments. It is hidden in a way that forbids closure. The universe allows massive, long-lived stellar remnants to exist without leaving a continuous observational trace. 22. Gravitational lensing and the illusion of completeness. Gravitational lensing is often invoked as the ultimate corrective to electromagnetic bias, a method that sees mass rather than light. At first glance, it appears to offer a way out of the epistemic trap described above. Yet a closer examination shows that lensing does not restore access to true stellar population statistics. It merely introduces a different, equally selective filter. Strong lensing detects rare, highly aligned configurations involving massive foreground objects and distant background sources. Weak lensing measures ensemble distortions averaged over vast populations, sacrificing individual identification entirely. Microlensing sits in between, capable of revealing compact objects, but only transiently, probabilistically, and without yielding a complete census. Moreover, lensing is blind to structure. It reveals mass along a line of sight, but not whether that mass belongs to a single object, a binary, or a higher-order system. Thus, even where lensing detects dark mass, it erases the very multiplicity information that would be needed to reconstruct stellar population statistics. 23. Limits of population statistics for star formation. If the true stellar population is fundamentally inaccessible, then population statistics cannot serve as decisive evidence for star formation mechanisms. At best, they describe the visible residue of formation processes filtered through time, evolution, detectability, and selection effects. Star formation theories often rely on present-day distributions, the apparent dominance of low-mass stars, inferred multiplicity fractions, or the relative scarcity of massive objects. Yet if large fractions of massive stars rapidly disappear into dark remnants, hidden binaries, or silent compact systems, the observed distributions no longer reflect formation outcomes, but survival outcomes. The methodological consequence is clear. Population statistics cannot function as primary arguments for star formation theory. They can test internal consistency, rule out extreme scenarios, or provide boundary conditions under explicit assumptions. They cannot uniquely select one formation pathway over another. 24. Objections and responses. Several predictable objections arise in response to the claim that stellar singleness cannot be established. It is important to distinguish between genuine objections and statements that merely restate the limits already acknowledged. A common response is that observational constraints on companions around many stars are extremely strong. This is not an objection. Strong constraints reduce regions of admissible parameter space. They do not eliminate it. Increasing sensitivity improves limits, but does not alter the logical structure of exclusion. It is sometimes argued that, while absolute singleness may be unprovable, it remains a reasonable practical assumption. This is a methodological choice, not a refutation. The present argument does not prohibit simplifying assumptions. It clarifies their epistemic status. A more substantive objection claims that if singleness cannot be established, then binarity becomes unfalsifiable. This objection misidentifies the claim. Binarity is not asserted as a universal fact, but as a standing possibility. It remains falsifiable in specific forms and configurations. What is rejected is not falsifiability, but exclusivity. In sum, no objection overturns the central asymmetry identified in this work. Companions can be discovered. Their absolute absence cannot be demonstrated. Recognizing this does not weaken astrophysics. It strengthens it by aligning its claims with what observation can and cannot support. 25. Conclusion. This article has argued for a single, carefully delimited claim. No observation of any individual star can establish with certainty that it is not part of a binary or higher-order multiple system. This impossibility is not a technological limitation awaiting future resolution, but a structural feature of astronomical inference that arises from the nature of parameter space, the logic of exclusion, and the physics of stellar systems themselves. The argument proceeded through several interlocking stages. We began by examining the observational methods available for detecting stellar companions, direct imaging, spectroscopy, astrometry, transits, and eclipses, and showed that each operates within a constrained sensitivity window. The failure to detect a companion using any method, or even all methods simultaneously, does not demonstrate non-existence. It demonstrates only that no companion exists within the explored domain. The space of possible binary configurations is continuous and unbounded, admitting companions of arbitrarily low mass, arbitrarily long period, arbitrarily unfavorable inclination, and arbitrarily high luminosity contrast. There is no natural boundary in this space that coincides with observational thresholds. Star formation theory reinforces this conclusion from a different direction. The collapse of molecular clouds is generically unstable to fragmentation, and multiplicity is observed to be common indeed, dominant among young stellar populations. While dynamical evolution can disrupt some systems, producing apparently isolated stars, this does not convert present-day non-detection into proof of primordial singleness. The Sun itself, despite being the most intensively studied star, cannot be certified as single. It serves not as a counterexample to the argument, but as its most instructive illustration. The epistemic asymmetry between detection and non-detection lies at the heart of the analysis. Detection is a positive existential claim that can be confirmed and retained. Non-detection is a failure to confirm, which carries evidential weight only if the space of alternatives has been exhaustively excluded. In astronomy, this exhaustion is impossible. Consequently, binary star and single star are not parallel categories. One names a discovered structure, the other names the absence of a discovery. Treating them as symmetric leads to systematic misinterpretation of stellar statistics. The implications of this asymmetry are far-reaching. Stellar catalogs must be reinterpreted. Entries labeled single represent lower bounds on isolation, not definitive classifications. Stellar and planetary models must acknowledge that hidden companions remain epistemically admissible in all cases. Multiplicity fractions reported in surveys are inclusive. They can grow as detection improves, but the complementary single fractions are not exclusive and carry no comparable stability. Claims such as, most stars are single, are not observational conclusions, but statistical inferences conditioned on priors and detection models that cannot be independently verified. The analysis extended naturally to several domains where the consequences are particularly acute. Anthropic bias introduces a selection effect. Observers are more likely to arise in systems where binarity, if present, is dynamically benign and observationally elusive, making our own solar system a poor basis for inferences about the prevalence of singleness. Black holes and other compact remnants represent the limiting case of epistemic opacity companions that can be massive, gravitationally significant, and completely undetectable except under rare and transient conditions. The existence of such objects implies that the true stellar population is larger and more structured than the luminous census reveals. This concealment has implications for galactic mass budgets. If significant populations of compact binaries and dark stellar remnants exist, they contribute to gravitational dynamics while remaining absent from star counts. Part of the missing mass at galactic scales may therefore be baryonic, but observationally silent, not exotic, but merely unseen. The sharp dichotomy between luminous matter and non-baryonic dark matter is accordingly less clean than is sometimes assumed. The systematic bias toward long-lived, low-mass dwarfs in stellar catalogs further distorts our picture of stellar populations. Massive stars burn brightly and briefly, then collapse into remnants that vanish from electromagnetic observation. The present-day census is therefore a survivorship sample, not a formation sample. Population synthesis models attempt to reconstruct the invisible past, but they do so by assumption and extrapolation, not by measurement. The true stellar population statistics of the universe are not merely unknown, they are in a precise sense unknowable. Gravitational lensing, often invoked as a mass-sensitive corrective to electromagnetic bias, does not escape the fundamental limitation. Microlensing detects events, not inventories. It confirms existence without constraining abundance. Strong and weak lensing sacrifice individual identification for ensemble statistics. None of these methods can close the census of dark stellar mass. The hope that gravity would reveal what light could not has been partially vindicated. Dark objects exist, but the deeper hope of completeness remains unfulfilled. The methodological lesson is clear. Population statistics cannot serve as primary arguments for star formation theory, because observed distributions reflect survival and detectability as much as formation. Multiple, Even radically different formation scenarios can converge to similar present-day populations once evolutionary attrition and observational blindness are accounted for. The arrow of inference from observation to formation is fundamentally underdetermined. Against this background, the rational stance is to treat binarity as a standing possibility rather than an exception requiring special justification. This does not assert that all stars are binary, an unfalsifiable and therefore unscientific claim, but that singleness cannot be established and should not be treated as the null hypothesis. The burden of proof is asymmetric. Binarity can be confirmed, singleness cannot. Epistemic prudence therefore favors models, interpretations, and classifications that are robust to the presence of undetected companions. The argument developed here is deliberately modest in its positive claims. It does not assert a specific multiplicity fraction, nor does it claim that any particular star has a companion. It asserts only that the category of the single star is not a physical fact about nature, but a provisional observational status, a label that reflects the current limits of detection, not the structure of reality. This distinction matters. It affects how we read catalogs, how we build models, how we interpret anomalies, and how we reason about stellar populations across cosmic time. More broadly, the analysis exemplifies a general pattern in empirical science. Positive existential claims can be established by observation. Negative universal claims cannot, unless the space of alternatives is finite and exhaustively searchable. In astronomy, where distances are vast, timescales long, and configurations continuous, this condition is never met. The lesson is not skepticism toward scientific knowledge, but precision about its scope. What is observed can be affirmed with confidence. What is not observed remains in many cases permanently undecidable. The night sky, viewed through this lens, appears differently. The stars we see are not isolated points, but nodes in a network of gravitational relationships, many of which are invisible. The binary fraction we measure is a floor, not a ceiling. The single stars in our catalogs are not proven solitaries, but unresolved questions. And the universe, taken as a whole, may be far more densely populated with stellar mass past, present, and gravitationally active than the luminous census suggests. Accepting this uncertainty does not diminish the achievements of observational astronomy. It clarifies what those achievements can and cannot establish, and in doing so, aligns our claims with the evidence that supports them. Acknowledgements. The author thanks Jose Caballero, Centro de Astrobiología, Madrid, for valuable correspondence and for drawing attention to Carmina's results on stellar singlicity constraints, particularly the work on GJ 486 representing the tightest observational limits on companion exclusion to date. His observation that a star is single until demonstrated the opposite precisely captures the conventional assumption this paper seeks to interrogate. Cite as Kriger, B. 2026. Can a star be proven single? Observational limits and theoretical implications. Zenado.